Deep beneath the serene landscapes of Oregon, a silent, unseen force is stirring. For months, sensitive instruments have been picking up a faint, persistent hum, a series of tiny shivers deep within the Earth's crust. Long before anyone on the surface felt a thing, seismic monitors along Oregon's ridgelines were recording these low-frequency tremors. This wasn't the violent shaking of an earthquake, but something more subtle, a rhythmic pulse that hinted at a fundamental change in the state's geology. In monitoring stations from Portland to Bend, scientists noticed the pattern. The quiet hum grew more consistent, prompting teams to intensify their fieldwork, unaware they were on the verge of uncovering a phenomenon of extraordinary speed and scale. The first concrete evidence emerged from deep monitoring wells, shafts drilled kilometers underground to track the state's geothermal pulse. Temperatures began to rise. At first, it was by mere fractions of a degree Celsius. But then, the rate accelerated. Within weeks, the increases doubled, then quadrupled. In some locations, the temperature jumped by over 1 degree Celsius in a single season. To you and me, that might not sound like much, but in the world of geology, it's a lightning strike. These deep geothermal systems are incredibly stable, with temperature changes normally unfolding over centuries, not weeks. Something was rapidly injecting heat into the system, and the speed of this change was profoundly abnormal. As temperatures rose, so did the pressure. Gauges spread across dozens of kilometers began to show synchronized spikes. This wasn't a localized glitch or an isolated pocket of activity. The pressure was building uniformly across a vast region, suggesting a single, powerful driver was at work. Instead of the chaotic, independent surges typical of Oregon's geothermal fields, this coordinated rise pointed to something much larger, perhaps a massive magmatic swell pushing up from below, pressurizing the entire system like a piston. This uniformity defied all historical data, signaling a geological reorganization on a regional scale. Meanwhile, high above the Earth, satellites were capturing another piece of the puzzle. Using a technique called interferometry, which can detect millimeter-scale changes in ground elevation, scientists confirmed that several of Oregon's geothermal zones were physically bulging upward. The uplift was subtle, just a few millimeters over 6 months, but the rate was several times faster than the normal seasonal flexing of the Earth's crust. The patterns of deformation were also unusual. Instead of a simple dome-shaped lift, the ground was warping in elongated shapes, hinting that superheated fluids were not just pushing up, but also migrating sideways through underground fractures, like a network of expanding veins. Back on the surface, Oregon's famous hot springs were putting on a show. Visitors and locals noticed changes. The bubbling grew more vigorous, the water became more agitated, and sediment was frequently stirred up, clouding the once clear pools. These weren't just aesthetic shifts, they were symptoms of deeper unrest. Gas monitors confirmed a significant increase in carbon dioxide and hydrogen sulfide, gases directly linked to magma and deep geological activity. In one remote basin, a sudden, powerful gas burst erupted from a spring. But unlike a typical release that vents pressure, the activity returned to its previous high levels almost immediately. The system was recharging with incredible speed, indicating that the pressure from below was immense and relentless. Beneath the surface, this pressure was fracturing rock. Micro-earthquakes, too small to be felt by humans, began occurring in rapidly increasing numbers. Over the past 6 months, clusters of these tiny quakes have lit up seismographs, mapping out a complex network of shifting stresses. Some sequences propagated sideways, tracing the path of migrating fluids, while others shot vertically, indicating that pressure was building from below. These patterns are eerily familiar to volcanologists. They mirror the seismic signatures seen in other volcanic regions, like Iceland and New Zealand, right before major hydrothermal changes or eruptions. So what is causing all this? All evidence points to a massive thermal pulse rising from deep within the Earth's lower crust. This isn't necessarily a classic magma intrusion, where molten rock pushes its way to the surface. Instead, scientists believe it could be a wave of pure heat, traveling through the semi-molten rock deep below. This heat wave is superheating vast reservoirs of underground water, causing it to expand dramatically and forcing its way into every available crack and fissure. This process, known as ductile heat transfer, creates immense pore pressure, effectively jacking up the ground from below and driving the frantic activity we're now witnessing. Similar behavior has preceded significant geological events in other major geothermal zones around the world, from Italy to Iceland. The most immediate risk isn't a volcanic eruption, but something equally dangerous: a hydrothermal explosion. When underground water flashes into steam with explosive force, it can blast rock, mud, and boiling water into the sky, carving out massive craters. Oregon's landscape is dotted with scars from such events in its ancient past. With pressures and temperatures building so rapidly, the probability of new steam vents opening or of a catastrophic blowout is a plausible short-term scenario. The ground itself could deform rapidly, posing a direct threat to anything or anyone nearby. The impacts are already beginning to ripple through local communities. As these pressurized, superheated fluids interact with shallow aquifers, they can alter the chemistry of drinking water. Some households near active zones have reported their well water developing a metallic taste or a stronger smell of minerals like sulfur. There's also a growing concern for infrastructure. Power stations, pipelines, and underground utilities built near these geothermal fields face long-term stress. Continuous uplift, even at a few millimeters per month, can strain foundations, warp roads, and rupture pipes. Engineers are now reassessing these vulnerable corridors, forced to plan for a future where the ground beneath their feet is no longer stable. Ultimately, the source of this anomaly may lie hundreds of kilometers away, deep beneath the Pacific Ocean. Oregon sits on the edge of the Cascadia subduction zone, where the Juan de Fuca tectonic plate is slowly sliding beneath the North American continent. This slow-motion collision is the engine that drives all of Oregon's volcanism and geothermal activity. Scientists theorize that even a subtle shift in the angle or speed of this subduction could be enough to redirect the flow of heat from the Earth's mantle, altering pressure across the entire crust. This could be the master switch that has just been flipped. What happens next is uncertain. Geological models present a wide range of possibilities. The system could slowly vent its excess energy and return to a stable baseline over the coming years. Or, this could be the beginning of a new era of heightened geothermal volatility that could last for decades, reshaping Oregon's landscape in ways we haven't seen in modern history. We are witnessing a geological system awakening from a long slumber, driven by forces that operate on a planetary scale. The tremors in the deep, the heat in the wells, and the bulge in the land are not isolated events. They are interconnected symptoms of a profound change, a reminder that the ground we stand on is not static, but a dynamic and powerful entity. The story of Oregon's geothermal anomaly is still being written, 1 millimeter of uplift, 1 degree of temperature, and 1 tremor at a time. Thank you for watching. Don't forget to like and subscribe for more deep dives into our incredible planet.